So this video is just going to go over the main key things that you need to remember for chemistry paper 1. So let's start off with topic 4, which was the recently top thing that we did in September. So the reactivity series you need to have in front of you, this is something you need to remember. So metals are found in ores, commonly as metal oxides. For example, sodium oxide, copper oxide. Before we move on to that, let's just go back to some key chemistry things that you need to know and understand. So finding the number of protons, electrons and neutrons of different elements, and then we'll look at how we can draw the atomic structure and electronic configuration. So let's use sodium as an example. So sodium has a mass number of 23 and a atomic number of 11. Now this is found on the periodic table, which you will have. Mass number is the number of protons plus neutrons, and the atomic number is the number of protons. And remember, the protons is the same as the electrons. So if sodium has 11 protons, it therefore has 11 electrons. And that's something important that you need to know when you're drawing the actual atomic structure. Now, if we know that the protons and electrons are both 11, how do we know the number of neutrons? Well, all you do is the mass number minus the atomic number. So 23 minus 11, which gives you the neutrons of 12. Okay, so you can have a go at doing protons, electrons, and neutrons for any other element by yourself for revision. But let's just move on to drawing the electronic structure. Okay, so we're going to draw sodium now. So sodium is in row 3 of the periodic table, so therefore it's in row 3, so it has 3 electron shells, so I'm drawing 3. And I know that the rule for the electronic configuration, how many electrons we can fit on each shell, is 2, 8, and 8. So the first one, we draw 2 electrons, second, 8. And then the outer shell, I know that the number of electrons is the same as the group it's in. So sodium is in group 1, so it has 1 electron on the outer shell. The other way you can figure it out is just looking at the atomic number, the electrons, and just doing 11 minus how many you've already filled up. Okay, so once I change the colors, the number of electrons, same as the group number. And this is what the atom is, but you also need to know what the ion looks like. So when a metal such as sodium forms an ion, because it has 1 electron on the outer shell and it needs to have 8 to be full and to be stable, instead of gaining 7, metals such as sodium, anything in group 2 and group 3, they lose electrons. And when you lose an electron, when the atom loses an electron, which is negative, it becomes positive. So sodium has 1 electron on the outer shell. It loses that 1 negative electron and forms a +1 charge. So it completely has lost the outer shell. And so it just has the 2 shells now. And then we show brackets and a charge on the outside to show that it's an ion. Okay, moving on then to ores again. So ores, like we said, are found as metal oxides. So copper oxide, you can have zinc oxide, and there's some metals like gold and silver that are found as native, so uncombined, just because they're so unreactive. So that's why we use gold and silver as jewelry, because then they don't react with water and oxygen like copper and iron would. So we do need extracting methods for metals such as copper and sodium, but we don't need to extract gold and silver because they are naturally found as uncombined. So they're not found as gold oxide, for example. The two extracting methods that you need to know is one, electrolysis, which is quite expensive because it requires electricity. So we only use electrolysis for metals that are more reactive than carbon, and we'll look at why. And then the second one is using carbon reduction, so heating the metal oxide with carbon, and that will extract metals less reactive than carbon. and let's look at an example. So the example that we're going to look at is a example of a displacement reaction. Now just go back to looking at what displacement means. So metals found in their natural uncombined state are not included in extracting metals. So reduction of an oxide by carbon, and we've done this practical as well. So because displacement reactions of carbon can displace anything that's less reactive from the oxides, if we heat the metal oxide, such as copper oxide with carbon, the carbon is more reactive, so it will displace the metal, which we can then extract, and then we form carbon dioxide. So here's the example that I've drawn, copper oxide plus carbon. How do you know this displacement? Well, if you look at the carbon on the reactivity series, it's more reactive than copper, it's above copper. So it displaces the copper. So after the arrow, the copper is going to be by itself because it's been displaced, and the carbon has bonded with the oxygen atoms and formed carbon dioxide. And this is displacement and also reduction. Reduction because we've removed oxygen from the copper. So reduction has two meanings. So one is removing oxygen and the other is gaining electrons. And this is how we did it in class. It's a very bad drawing, but this is how we did it in class. And then the other extracting method is electrolysis. And this is only for very reactive metals. Why? Well, because something like sodium, which is more reactive than carbon, cannot be displaced by less reactive. So it cannot be displaced by less reactive carbon because it's more reactive. So sodium can only be extracted, or anything that's more reactive than carbon, like sodium, potassium, can only be extracted by electrolysis, which is very expensive. And now we look at how electrolysis is carried out. Okay, so what does electrolysis mean? So using electricity to split ionic compounds. And again, this is expensive. So let's show this in a diagram. Again, a very not pretty diagram, but you'll get the message. So we have an electrolyte. Now an electrolyte is a molten or aqueous ionic compound. Now it has to be molten or aqueous because if it was a solid, it would not conduct electricity. So we have our molten or aqueous ionic compound like sodium oxide. It's ionic because it's a metal and a non-metal. So we melted it, or we've dissolved it in water to form aqueous, and that's called an electrolyte. Then we will have two electrodes. One's a cathode, one's an anode. And then I'll draw that in just a second. So we have two electrodes, one's cathode. So we have two electrodes, a cathode and an anode. Just remember, panic positive is our anode and our negative is a cathode. So these two electrodes are connected to a battery, and we can test that the electrolysis apparatus is actually working. We did this in class by connecting these wires to a bulb. And when the bulb lit up, that meant that our practical was working. And if it didn't lit up, that could be maybe there's a fault in the battery, the bulb, or the wires are not connected properly. But using a bulb to light up will show that it's actually working. And this symbol is how we draw a battery. How do we draw the symbol for a bulb if we wanted to show this in the diagram? So bulb, we draw like this across, and you can add that to your diagram as well, just to show that this is how we did it in class. So this is a simple diagram of electrolysis which you need to know. So we have two types of electrolysis, aqueous and molten. So you can pause this video to have a look at the two different types. So with molten electrolysis, so we've got the anode and cathode. The negative ions move to the anode because opposites attract. So our bromide ions in this example of copper bromide would move to the anode, lose electrons to form our non-metal, which is bromine gas. You can show this as a half equation as below. And at the cathode, because it's negative, our positive metal ions move to the cathode and gain electrons and form the metal atom at the cathode. So a metal forms at the cathode, non-metal gas, for example bromine, forms at the anode. With these examples, how you can remember it is as anode, what the product will be the non-metal. So if we had a copper bromide example, the non-metal in that formula is bromine. So bromine would form at the anode, and at the cathode, it's the metal that forms. So the metal in that formula is copper. Copper is the metal. It's on the left. So copper forms at the cathode. And this is just a half equation to show it. With aqueous, there's a rule that you need to know. Because we've dissolved the ionic compound in water, so there's a rule that you need to know, because there's hydrogen ions at the cathode now, just because hydrogen is also positive. So if hydrogen is also at the cathode in aqueous, you need to remember that only the less reactive positive ion forms, because the less reactive it is, the more easy it is to gain an electron. Remember at the start when we said that metals lose electrons to form ions. Now in electrolysis, the metal ion has added an electron because of electrolysis. So we've added electron to the metal. If it's less reactive, if the ion is less reactive, it's easier to add an electron. So it has to be less reactive than hydrogen in order to gain electrons and form an aqueous electrolysis. So metals below carbon can form in aqueous, but metals above carbon, like potassium to aluminium, cannot form in aqueous electrolysis. So they cannot be extracted using aqueous. You have to use molten electrolysis. That's why the extraction of aluminium oxide is done in molten aluminium oxide, not aqueous. The anode aqueous half equation for anything that's not from group 7 is here. It's very complicated, but all you need to know is if we have something from group 7, so if we have our non-metal from group 7, then it loses electrons, forms the non-metal, example bromine. But if we don't have something from group 7, we don't have the non-metals from group 7, then the hydroxide that's come from the water loses the electron and forms water and oxygen gas. So whatever does not form at the cathode or anode is remaining. These are the products remaining. They'll most likely either remain in the electrolyte at the bottom, or if it's a gas, it will then evaporate, dissipate. But you do need to show that as well, so you need to understand that. So in this example of copper sulfate, because copper was less reactive than hydrogen, it did form at the cathode. So the product left over was sulfuric acid, and the other product that was left over was hydrogen at the cathode and sulfate ion at the anode. So in this example of electrolysis of aluminium by electrolysis, aluminium is more reactive than hydrogen, so we cannot use aqueous electrolysis, so we stick to the molten electrolysis. Now, aluminium oxide has a very high melting point, so that's why it was mixed with bauxite or cryolite to lower the melting point. Have a look at that example, and you will see that the cathode is exactly the same. You gain electrons on the metal ion, and at the anode, you lose electrons from the non-metal ion. So, going on to acid reactions, and these are just some general word equations for different acid reactions. And I'll do one example. So sodium plus hydrochloric acid will form a salt, sodium chloride, and our hydrogen. Now, when you're naming the salt, which is formed in each of these neutralization and acid reactions, just know that the first name of the salt comes from the metal, so sodium. Second part comes from the acid you use, so chloride for chloric acid, nitrate for nitric acid, and sulfate for sulfuric acid. Ionic equations is something that can be quite tricky, but we'll look at one example now. So this is a reaction between magnesium and sulfuric acid. So before we do this, let's just look at how we actually write symbol chemical formulas. And I like to use the double cross method. So have a look at this one. Sulfuric acid, hydrogen is a +1, sulfate -2. Charges are not the same, so you cross the numbers over. So I've crossed the 2 on the left and the 1 on the right. So when I rewrite it, it's H2SO4. And this is what we call the double cross method or the cross method. So when we have magnesium in this formula, you can see it's not combined with anything else. So we don't have a charge. This is just our atom. So we just write 0. You don't have to write this, but I've just wrote it. And our hydrogen, because it's combined with sulfate, so you have to write the charge with hydrogen. Because it's in group 1, it has a +1 charge. So I'm just going to write plus. And there's 2, H2, but I'm not going to write H2, little 2 next to it, because that's changing the formula. So I'll just write the big 2 in front. Then the magnesium is in group 2, so the charge is +2. Hydrogen is not combined with another element, it's combined with itself. So again, it doesn't have a charge, so it's 0. And just remember, hydrogen, like chlorine and oxygen, is diatomic, or anything from group 7 is diatomic. And you can look back at the simple covalent structure of this. Hydrogen shares a pair of electrons because they both need to complete an outer shell. And so it exists as H2, so it comes in 2s. So how do you know if what's been oxidized, what's been reduced? The magnesium has changed from magnesium with no charge to magnesium +2 after the reaction. And the only way it can do that is if it has become more positive, and it only becomes more positive when it loses negative. So it's lost a negative electron. Because the charge is +2, it forms a +2 ion charge. It has lost 2 electrons. And remember, after the arrow means it's lost. Now hydrogen started off as positive ion, but after the arrow, it's now gone to being neutral, nothing, no charge, H2. So we go from positive to 0, +1 to 0 by subtracting. So we have gained a negative electron. Again, it's diatomic, so that's the only reason why I've got the 2 in front, because I need to balance it on both sides, and therefore you have to gain 2 electrons. So oxidize, lost, reduced, gain electron. And this is just another example of how we write ionic formulas or writing the chemical formula. And an easy example is sodium oxide. So the sodium has a +1 charge, oxide has a -2 charge. Charges are not the same, cross the numbers. Okay, so after we did that in class, we did this practical, which is the copper sulfate, making copper sulfate crystals practical. Now, it doesn't just have to be copper sulfate crystals. It could be anything, as long as it's an insoluble base. We react it with an acid, and then we use filtration and then crystallization to make our crystals. So it could be, for example, an insoluble base of zinc oxide. We react it with sulfuric acid, and we'd still make a soluble crystal of zinc sulfate. Or it could be magnesium oxide with sulfuric acid. We'd make magnesium sulfate. Or magnesium oxide with hydrochloric acid. We'd make our magnesium chloride crystals. So the name could be anything, but the method and the steps remain the same for making a soluble salt from an insoluble base. So first thing we do is we add excess of our base because we want the reaction to complete. We warm the acid to speed up the reaction. And then we dissolve it until no more can dissolve. And then to remove any undissolved of our base, copper oxide, we use filter paper. The filter paper traps the residue, traps the undissolved solid, and it lets the copper sulfate solution pass through. And this is how it looks like. After we do that, to remove the water in the copper sulfate solution, we gently heat it using a Bunsen burner or a water bath, and this will make the water evaporate and it will leave the crystals to slowly form after it's left to cool. And you need to justify each part of it. So why did we use excess? Well, to make sure the reaction is complete. Why did we warm the acid? To speed up the reaction. Why did we use filter paper? To remove undissolved solid. And then why did we heat it? Well, to evaporate the water. So this is a required practical that we have done in class, and you need to know the full method. Okay, so just moving on to another practical we did, which I think would be useful to cover again, is the titration. You can watch a video on titrations again if you've forgotten what it looks like. But I just want to focus on the titration calculations, which I think we did struggle with in class. So I'm just going to copy this question over down here. Paste. So here's a question. In a titration experiment, 20 centimeters cubed of potassium hydroxide is used. In 1 mole per decimeter cubed of hydrochloric acid with a volume of 12.5 centimeters cubed. So I'm just circling the main parts. And the first thing I'm going to do is write the symbol equation. Sometimes it'll be given to you, sometimes it won't. But it's nice and easy because the formula has been given, so I'm just going to react. I use my general equation. So potassium, first name, chloride, KCl, charges are the same, so it's just KCl, and water as the other product. Then I just check its balance, and I can see it's balanced. And now I can then do the molar ratio. Now to find the molar ratio, you look at the number in front of the formula. Now because there's no number here, this means that there's 1. So there's 1 of potassium hydroxide to a ratio of 1 of HCl. So the molar ratio is 1 to 1. Okay, now with titration, it involves concentration equation, which is concentration equals moles divided by volume. You need to know the units of volume. This is very important. Volume can be given to us in centimeters cubed, but we want to convert it to decimeters cubed. To convert that, you divide centimeters cubed by 1,000 to get to decimeters cubed. So therefore, the units for concentrations are mole per volume because it's mole divided by volume. So let's look at our question. I like to split it into the alkali to the acid. It makes it easier. So I'm going to write moles equals for both sides, volume equals for both sides, and concentration equals for both sides. Then I'm going to look at my question and I'm going to pick out the information I can. And remember, this is the exact same method that we use for the other calculation that we did with moles and mass and MR. So it's the same method, and I think it's a lot easier to do it this way. So the volume of my alkali was given to me as 20 centimeters cubed. I'm converting that to decimeters cubed. So 20 divided by 1,000. I'm doing this in my head because I can't find my calculator, but you will have a calculator in the exam. So double check that's right, 0.02 decimeters cubed. And then the volume of the acid is 12.5. So 12.5 centimeters cubed to decimeters cubed should be 0.0125 decimeters cubed. So I've got my volumes for both. Let's see if I can have a concentration. So concentration, I've only have of the HCl, which is 1, a nice easy number. So 1 mole per decimeter cubed is a concentration of the acid. So I'm just going to write that there under the acid column. And looking at the question, they haven't given me a concentration of the alkali. That's because they want me to work out the concentration of the alkali. So you can see which side is more complete, the right. So we're going to use the right side numbers to find the moles. To do that, I'm going to use this equation and I just rearrange it. So moles equals concentration times volume. So 1 times 0.0125, I don't even have to use a calculator, that's 0.0125 moles. I know the molar ratio that I said at the start is 1 to 1, so I can just take that to the other side. So the moles of the alkali is also 0.0125. Now, I can now work out the missing concentration by using this equation, moles divided by volume, so 0.0125 divided by 0.02, and that will give me an answer. I worked it out at the top because I can't bother to use a calculator. Scroll up. Is 0.625. So 0.625 moles per decimeter cubed is your answer. And that is how you do titration calculations. Have a look at the Unit 4 booklet. You will find other examples in there. And you can use the exact same layout, exact same method. Just remember the equation and don't forget to convert volume units. Okay, moving on to something else. Let's see. So let's go back to topic 1. Actually, no, topic 2, which is in year 9. You've done so atomic structure, finding protons and electrons and neutrons, and then we'll look at bonding as well. Okay, so just to recap, mass number is the protons plus neutrons. And this can be used to work out relative formula mass. So relative formula mass, I like to say, is the total of the mass numbers in a formula. So let's use something as an example. Let's see. So let's use sodium oxide as an example. So use your periodic table to find the mass numbers of sodium and oxygen. So on the periodic table, you will see that the mass number of sodium is the bigger number, which is 23, and mass number of oxygen is 16. So your relative formula mass is you're going to add up these mass numbers. There's 2 sodiums in this formula, so you have to do 23 times 2 plus 16, and that will give me an answer of 52. And that is how you do relative formula mass. So the other thing you need to do with mass numbers is something called relative atomic mass or relative abundance of isotopes. Because isotopes don't have the same number of neutrons, the mass numbers will be different. So we have to work out a relative abundance using percentage and the mass numbers. So sometimes in questions they lay out like a table like this. I'm just going to draw an example. I don't have my calculator, so I'm just going to give you an estimate of this answer, but you can do it properly using your calculator. So if you were given these 2 isotopes, chlorine 35, chlorine 37, the numbers next to it is actually the mass number in the question, and then you're given a percentage. To work out the relative atomic mass, you times the mass number by the percentage, add it to the other mass number times the percentage, and then you divide it by 100 to get your answer. So I'm just going to estimate that this answer is around 37.5. Remember to always show you're working out. Okay, let's move on to working out moles, which I think is another tricky calculation, but which can easily get you lots of marks. Okay, to work out moles, you need to know the equation. Moles equals mass divided by mR. Now, mR just stands for the relative formula mass that we've just been working out. So, let's look at an example of work out the moles of 5 grams of sodium. Now, the sodium, you just need to know the mass number because it's not an actual formula, it's just by itself. So the mass number of sodium you get from the periodic table, which is 23. So the mass equals 5. 5 divided by 23 will give you your answer of your moles. Okay, so this will get a bit more challenging when you're getting questions which says, using the moles equation, work out the unknown mass of the reactant or product using a known mass. So then you use the molar ratios and you use this equation to rearrange it to find the missing mass. And let's look at an example together. Example we can do is our titration example again. So potassium hydroxide plus HCl forms potassium chloride plus H2O. So the formula is important that you balance it, because remember those numbers in front, what do they mean? The molar ratio. Okay, so the molar ratio is very important in this question, in this working out for mass. So again, let me just make up a question. 5 grams of potassium hydroxide was used. Work out the missing mass of, it could be anything in this formula. So let's do the HCl. Because we know the molar ratio is 1:1, if we work out the moles of one thing, we can just move that to the other side, use this moles of that to work out the moles of something else because of the ratio, and then we rearrange it to work out the mass. So let's work out the moles of potassium hydroxide because the mass of that is given. So I'm going to write 3 things under each column: moles, MR, and mass. And then the other side, the same: moles, mass, MR, and mass. You'll notice that this method, this like column thing method, is the exact same that we do with titration. And I think working out like this makes it just a little bit more clearer and easy to do. So 5 grams MR of potassium hydroxide I worked out to be 56. So to work out the moles, I'm going to divide 5 grams divided by 56. And that's going to give me my answer of my mole. Bear with me while I put this in. So 5 divided by 56. And you could do this on your calculator. Is 0.09. So I'm just going to round it to 0.09 moles. So I know there's 1:1 ratio, the numbers in front. So that means the moles of HCl is also 0.09 moles. Okay, so MR of HCl, nice and easy, is 38.5. 37.5 plus 1, so 38.5. And then to work out the mass, I'm going to do moles times MR because I've rearranged my equation. And then that will give me a mass of HCl of 3.46 grams. So that's how you do working out mass. Okay, so like I said, let's go back to looking at bonding, which can be quite tricky if you don't know how to recognize which bonding is for what. Now, just remember, for ionic, it's always between a metal and a non-metal. If you don't know what's a metal, what's a non-metal, look at your periodic table. Metals are on the left, non-metals are on the right. So after usually the third group, it'll become a non-metal. Okay, so metals lose electrons to form positive ions. Metals are losers, remember that. Why? Let's have a look at the atomic structure to tell us why. Now, with sodium, it has 3 shells. We know that because it is in row 3. It has 2 electrons on the first shell, 8 electrons on the second shell, and then it has 1 electron on the outer shell. How do I know it has 1? Because it's in group 1. Then how can that group tell me how many electrons it's going to lose or gain? Well, 1 electron on the outer shell means it's going to lose 1 electron. So what charge will it form if it loses 1 electron? Keep that in your head while we draw the structure of chlorine. Now, if we had ionic bonding between sodium and chlorine atom, let's draw both of them first. So chlorine has 7 electrons on the outer shell because it's in group 7. Okay, so chlorine needs 1 more electron, which it's been given because sodium donates it. So when we redraw the ion, because sodium's lost the outer shell because it's donated the electron, it now only has 2 electron shells. To show that this is now an ion, because we've lost the electron, so we do +1. Why? Because electron is negative. So we've lost a negative electron. We've lost one negative electron. So the charge of the ion is +1. This is why metals are positive ions. They lose negative electrons. With the chloride ion, just remember when it's ion, the name changes. It's gained one negative electron. So it's gained one negative electron. The charge of this ion will be -1. Again, you show this using a bracket, and the charge is displayed on the outside. For revision, why don't you do another example of ionic bonding? Do sodium oxide, for example. That would be a good one. So sodium oxide. Just remember the rule for drawing electronic configuration 288. So 8 means that it's full and stable. If the atom does not have 8 electrons in the outer shell, it will react. So in ionic bonding, metals lose electrons to gain a full outer shell. Metals lose electrons to form a full outer shell, whereas non-metals gain the electrons to form a full outer shell. So this is why noble gases, which have 8 electrons already in their outer shell, don't react, because they don't need to react. They already have a full stable outer shell. So the properties of ionic compounds, because we formed these positive and negative ions, opposites attract, and this is called strong electrostatic attraction. Strong electrostatic attraction. This, therefore, means there's a high melting and boiling point with ionic compounds. So remember when we were talking about the aluminium oxide, when we melt it, we require lots of energy in electrolysis, which is expensive. Because of the strong electrostatic attraction, it requires lots of energy to overcome. They only conduct electricity when it's molten or aqueous. Let me show you why. So remember, with ionic bonding, there's a giant ionic lattice. It looks like this. I'm going to attempt to draw it neatly. So my purple is my metals, green is the non-metals. Opposites attract. Solid, regular arrangement. This is a solid ionic compound. You can see that if it's a solid, can the ions move? No. If the ions cannot move, it cannot conduct electricity. So therefore, it's important that we either melt or we dissolve it in water, because that will change the arrangement and that will make it easier for the ions to move and then carry the charge to conduct electricity. Right, moving on to covalent bonding then. Covalent bonding is between non-metal atoms that share a pair of electrons to complete a full outer shell. Now, something that people forget is silicon dioxide is also covalent. People sometimes think that silicon's a metal. It's not. It's a non-metal, and so silicon bonds with oxygen, and that's also covalent bonding. Okay, so the simple covalent molecules like chlorine, water, hydrogen, ammonia all look like this. So how I like to remember covalent bonding is like a Venn diagram. It looks like that. So the simple molecules are like water, carbon dioxide, chlorine, halogens, mainly group 7, and these have weak intermolecular forces, so the melting and boiling point is quite low. They do not conduct electricity because there's no delocalized electrons and there are no ions that are free to move. The other covalent bonding molecule is giant covalent molecule. That's a mouthful. And these, I'm just going to show you the 4 you need to know, are diamond, graphite, Buckminster fullerene. I'm probably spelling this wrong, so just double check. And silicon dioxide. So the diamond has 4 carbon atoms, so it's very strong. It's used as cutting tools. I'm going to try to draw the Buckminster fullerene. This is a terrible diagram, so just Google a picture. That will be much better. It kind of looks like a football. So it's like a ball shape, and this is because it's often used in drug delivery. So drugs are like encapsulated inside, and it's used to administer patients with drugs. Now, it's a giant covalent molecule because it has lots of atoms covalently bonded together, so it still has a high melting and boiling point. And then our graphite is the unusual one because it has three carbon atoms covalently bonded together. Many three carbon atoms covalently bonded together. So because it has three carbon atoms, it has a delocalized electron that can move, so it can conduct electricity. So graphite can be brittle, so it's used in pencils and lubricants because it can, the layers can slide. So it's unlike diamond, which has four carbon atoms covalently bonded together, so it's very hard. Again, it has very strong covalent bonds, very high melting and boiling point, and is also used as a cutting tool. Okay, silicon dioxide is the last one. So silicon dioxide has silicon bonded with many oxygen atoms. The structure, you don't need to know the structure because usually it's given to you as a diagram, but you just need to recognize that using the diagram, should be able to tell that this is a giant covalent molecule. Now I'm just going to draw what it looks like. This is again not the best drawing, but you can see that because it has many atoms bonded together, it's a giant covalent molecule. Okay, so the last bonding we're going to look at is metallic bonding. Now, metallic bonding is exist in metals. Again form a structure like this. We have a positive metal, and then the negative delocalized electrons. So what happens is that these delocalized electrons surround the positive metal atom, and they have strong electrostatic attraction because it's still opposites attract. So, just like with ionic compounds, they also have a high melting and boiling point. But metals can be malleable because the layers can slide. We can also form alloys if we mix different metal atoms, and because the sizes of the metal atoms are different, it will look like an irregular arrangement, and this makes it harder for the layers to slide when a force or pressure is applied. So that's why alloys are a lot stronger, and that's why they have lots of uses. So the last topic we did was energy changes, and this was the most recent topic we did. So topic number 5. With energy changes, there's two types, endothermic and exothermic. Just remember, endothermic means energy in, exothermic energy out. You do need to know the actual scientific definition. You cannot just say energy in, energy out. But we can draw a reaction profile diagram to represent this. So, on your reaction profile diagram, you have two axes. You can say course of reaction, and then on the Y is the energy that we're showing the energy change. So we have a reactant and we have a product. So reactant is at the bottom for endothermic because it will have less energy, and the product has more energy than the reactants, so it'll be at the top. Why? Because energy is absorbed from the surroundings into the system, so that's why the products end up with more energy than the reactants. So when we're showing this, the energy change is going up because energy is being absorbed into the system, into the reaction. Now you can see that the top peak on this curve has a name, has a keyword. This is the keyword for the minimum amount of energy required for a reaction to start, and this is called the activation energy. Now, different reactions will have a different activation energy. Let's draw this same thing, reaction profile, but for exothermic. How will the exothermic one look? Well, we have the same axes. So progress of reaction and energy. We have a reactants and products. Because with exothermic, energy is being released to the surroundings, so out, the reactants will have more energy than the products because energy that was in the reactants has been released into the surroundings. So when you're drawing this, it will look something like this. Again, you need to label the energy being released. You can show this with an arrow going down. And again, label the activation energy as well. Something else we also looked at is the effect of a catalyst on a reaction. So catalysts lower activation energy, and you can show this on your graph by showing another curve that has a lower activation energy. Now catalysts are unused and unchanged, and they work by providing a alternative pathway with a lower activation energy. So the required practical in this topic was the polystyrene cup one, where we measured temperature change to figure out if it's an exothermic or endothermic reaction. So I'm just going to use a diagram to show what we did. We used a thermometer to record the temperature at the start of a reactant. We noted this down. And then after we added our second reactant, we measured the temperature at regular intervals and noted this down. So first thing we did was measure the initial temperature change. After we do this, we add our second reactant. We stir, and then we record the temperature at regular intervals. For example, in class, we did this every minute. We recorded the temperature. So we should see a temperature change, either the temperature increasing or decreasing. If the temperature has increased, this means that energy has been released into the surroundings, therefore it will be exothermic. If the energy has decreased, this means that energy has been absorbed into the system, so this is endothermic. And we could present this as a graph with two lines of best fit. Okay, so the last thing we'll just quickly look at, and you can look at a better exam question, because with working out bond energies, they give you the reaction profile, all of this displayed formula. You don't have to actually know it, but I'm just going to draw one just as a example. But this will be given to you, so you don't have to worry about drawing this. What you need to know is making is exothermic and breaking is endothermic. So you will be given a table with the bond energies for each bond. And then what you have to do is work out the energy going in and the energy out by looking at this table and then adding up the total on the left and the total on the right. So example, the carbon and double bond oxygen is 147. Look at my reaction displayed formula, and I can see there's two carbon oxygen bonds, so I do 2 times 147, and that gives me an answer. I do that for each bond, and then I work out an answer on the left, which is the energy in endothermic, and then an answer on the right, which is the exothermic. Then I subtract that to work out the change, and then I get a final answer. Now, a way to remember if it's endothermic or exothermic is MEXPEN. Now, making bonds is exothermic. So, if making bonds is exothermic, meaning energy is released, that means you'll have less energy. There will be less energy in the products. So, we have minus an answer in kilojoules. if you look at the side that has more total energy, you will see that the right side will have more energy than the left side in, and that will make it a negative number. So that will make it exothermic. And then breaking bonds is endothermic. Why? Because well, you need energy to break bonds, so that's endothermic, and that will be a plus, a positive number, not negative. So fuel cells is something that you can do for revision. This is using hydrogen reacting with oxygen to make water, and this releases energy. You can have a look at your notes for this one. I won't spend too much time on this because I do want to go back to topic 4 again, just recap on some cool things. Okay, so going back to topic 4, the chemical changes topic, I just want to look at displacement reactions again. So we looked at an example of displacement reaction in the extraction of metals using carbon reduction. Because carbon was more reactive, it displaced the less reactive metal. Now, displacement reaction is when a more reactive metal can displace a less reactive metal. For example, if you didn't know the position of magnesium and copper on the reactivity series, how do you know which one's more reactive? You can see that the copper has been displaced by the magnesium because a new compound has formed. This is because the magnesium displaces it, kicks out the copper, and then reacts with the sulfate in the compound, and then the copper is displaced because it's less reactive. So if you didn't know which one was more or less reactive, just look at the formula and see which one's now being displaced, is not bonded to anything anymore. That's the one that's less reactive. We did this in class. Even when we didn't know the reactivity series, we used predicting reactions to figure out which one's more reactive. So we did the measuring the temperature change of a reaction. Obviously, the more reactive it is, the higher the temperature change. We also looked at the effervescence, which means the fizzing. If we could see more effervescence, that told us it was more reactive. How we did this was by reacting different metals with an acid, which would seen as fizzing, or we also did it with water as well. So that's how you would do a practical to predict reactivity of metals. Okay, now I said that there's 2 types of extracting methods, electrolysis and carbon reduction. Now the one, there's not 3 because unreactive metals that are native, like gold and silver, do not require to be extracted. Okay, so just want to go back to this. So have a go at doing lots of word equations for the acid reactions because that can come up. So all of these notes I will put on EduLink for you because I think it's good to show you how revision notes look like. But for revision, I would recommend that you do some calculations in the Unit 3 booklet. So everything after you do your mind maps and your flashcards and your memory notes, it's really useful to do practice questions so that you can see how you would apply your knowledge to actual questions. So there's lots of resources out there. You can use your CGP to answer some questions on there. I've emailed practice questions to you and the rest are on EduLink, so use them. And there's other much better videos than this on YouTube as well that you can use that have clearer notes. I would use them as well. But this video is just a summary of things that our class struggled with over this year. So it does not cover everything, but I think it's nice to see the key points from each topic. And hopefully this video has been helpful with that. So the last thing I want to say is good luck with your exams. And if you need anything, just let me know. And happy revising. Bye-bye.